Yeah. So, hello and welcome on behalf of St. Xavier's College, Ahmedabad, and the Astronomy Department, Astronomica, to the fourth and final day of our webinar, Antariksh, a webinar for curious minds. Today we have with us Dr. Vishal Joshi, and he will be talking to us on the topic of evolution of the sun. And I would request Sakshi Trivedi, member of our club Astronomica, to introduce Vishal Joshi, sir. Over
Thank
to you,
you.
Sakshi.
Thank you, Neilbhai. Hello and good evening, everyone. First of all, I would like to welcome Dr. Vishal Joshi, sir, who is currently working as a scientist in the Astronomy and Astrophysics Division at the Physical Research Laboratory. He has been working in the field of astronomy and astrophysics for over 12 years. During his research career, he has made significant contribution to the understanding of various physical, vital, and geometrical aspects occurring on and around nova, supernova, and other variable stars using ground and space-based observations, models, simulations, and theory. After getting his master's degree with gold medal in physics from Saurashtra University in 2004, Dr. Joshi joined PRL as a research scholar. He completed his PhD on observational studies of magnetic cataclysmic variable stars. He won postdoctoral fellowship award at prestigious institute Inter-University Center for Astronomy and Astrophysics, IUCA, Pune, where he obtained valuable experience in the field of astronomical instrumentation. He joined PRL as a scientist from January 2016 and has published more than 30 research papers in very reputed international journals, including one in the Nature, which is the most prestigious journal in scientific research. He uses many large telescopes like the Mount Abu Infrared Telescope, Himalayan Chandra Telescope, European Very Large Telescope, Infrared Telescope Facility in USA, and the Hubble Space Telescope for his research. He has significantly contributed towards computational astrophysics and automation of data analytics. He has prepared automated data analysis pipelines for several instruments used worldwide and is currently working on the project to commission the 2.5 meter class telescope at the Mount Abu Observatory, which is going to be the second largest telescope of India. He is a member of the International Astronomical Union, Indian National Science Academy, Astronomical Society of India, Gujarat Mathematics Association, and the Gujarat Science Academy. He is also very active in science popularization and has delivered more than 150 popular lectures and conducted more than 50 workshops on various scientific topics on astronomy, physics, and mathematics across the country. He is associated as an advisor and resource person with Science City Ahmedabad, Regional Science Center Rajkot, Narmada Nagar Community Science Center Bharuch, and Vigyan Nagari Bhavnagar. Now, I would like to invite Dr. Vishal Joshi sir to enlighten us about the evolution of the sun, the death of the living God. Thank you. Over to you, sir.
Yeah. Thank you, Sakshi, for my not so brief introduction. Thank you. And I also thank Astronomica to arrange this workshop so that, we can interact the young minds of your college and maybe across the state or the nation. So, as you know, the title of my talk is The Evolution of the Sun. Let me share my screen first. Okay. Is my screen visible?
Yes, sir.
Great. So so the title of my talk is The Evolution of the Sun, the Death of the Living God. We all know that if there is a God, of course, one of the God for us is the sun. If the sun was not there, we could not have been here. But the question comes, how the sun, comes into the picture and how it will go away. I will not talk about how sun formed, the birth processes of the sun. But being a Joshi, I will talk about the future only. That is how sun will evolve with time. Pardon me if I cannot justify this topic also in this 45-minute talk, because the evolution of not only sun but evolution of stars in general. I used to take a series of lectures for our PhD students, and still myself and my students feel that okay, yeah, this topic is not completely satisfactorily covered kind of. So it's extremely deep topic. I may not be able to touch upon many aspects of the stellar evolution field, but still I'll try to convey the real scenario, the real picture of the evolution of the sun-like star. So as you see here in this picture, the sun is a ball of hot gas. More technically, it is not ball of hot gas, it is ball of hot plasma. Because sun and all the stars and most of the interstellar medium and almost everything in the universe is made up of plasma. 99.9% of the material in the universe is made up of plasma. We are living in an exceptional, part of the universe where plasma is rare and solid, liquid, and gas is more common. How this huge, gigantic ball of plasma, stabilizes? So we all know about this common picture, which is called hydrostatic equilibrium. Our atmosphere also follows the same, more or less, same principle, and sun and other stars who are stable, all stable stars follow the same principle. The principle says that take any layer, any envelope of the interior of the sun, and the gravitational push towards the center and radiation push outside. So whatever you say pull and push, it's up to you, but both the forces, gravitational inward force and radiative pressure outward force, they compensate each other at different layers, different envelopes of the sun. So sun stabilization, it is neither collapsing under its own gravitation nor expanding under its own radiation, because both these forces are balancing each other. Talking a little more about the structure of the sun, I'm sure somebody else in this lecture series earlier must have discussed this part, but let me repeat it again quickly. So start with the center, the core of the sun, and we know that is the real powerhouse. We usually believe that the center of the sun is hot because some, or let us say technically, the fusion, hydrogen fusion process keep going in the center of the sun. Let me tell you, this is actually a totally wrong concept. It is actually otherwise. Core is not hot because of the fusion process. It is otherwise. Fusion process going on in the core because core is hot. Even before fusion process start, core was hot. When sun just started reaching in this shape, the core become hotter, and then the fusion process starts. Even if today we stop the fusion process at any say point of time, the star will start collapsing maybe after a few million years. But star will start collapsing, and the collapse of the star will release the gravitational potential energy, and that will again make this core hotter. So what kind of process is going on? The process is going on is called hydrogen fusion process. I hope all of you have studied this process. That is actually the fusion process of 4 hydrogen nuclei. Hydrogen nuclei are pure proton. So fusion of pure proton into 1 helium. And this is the one most famous cycle called pp chain. So proton merges into H2 and so on, and eventually H3 will form, helium 3 will form, and they will fuse to produce helium 4. In the process, again, hydrogen and the radiation in all the steps, this gamma rays will keep emitted. So total 6 hydrogen nuclei takes part in this process. 2 will get ejected to eventually 4 nuclei have participated, and we get helium stable nucleus, which comprises 2 proton, 2 neutron. And in this process, if you see, the mass of 4 hydrogen nuclei and the mass of 1 helium nuclei has some difference. And the difference of mass is converted into energy, and that energy is barely 4.3 10 to the power minus 12 joule. Number appears very small, but remember, at any point of time, at every second, within the stellar core, sun's core, 10 to the power 38 such processes keep going, and because of this process, sun is losing its 4 to 5 million ton mass every second. This number again appears very big. Sun is losing mass every second, almost 4 to 5 million tons. Million tons, yeah. So in that way, sun will, lose its most of the mass very soon. But that's not true. Even at this rate, after 1 billion years, sun will barely lose 0.1% of its total mass. So sun, you can imagine how heavy the sun will be. The mass of the sun is almost 2 into 10 to the power 30 kilogram. Which is almost equivalent to just less than a million Earth mass. So sun has so much of material within it, even at this high rate of process, it will not lose significant mass during its, even after the end of its life. Yeah. Okay, so in how much big part of the sun this process going on? Even for the sun right now, the process goes barely 0.3 fraction of the radius. So 30% of the radius. The core size is less than 4% of the total volume of the sun. The volume of the core is barely or even less than 4% of the total volume of the sun. So it's like, a person is earning and whole family is, spending kind of a situation. A small core is, earning all this radiation, producing all this radiation, and this, huge volume and large surface area is keep losing it exactly at the same rate. The rate at which the process occurs is equal to the rate at which this radiation is, lost by the sun. Another interesting process is called CNO cycle. CNO cycle is again the same hydrogen fusion process in which 4 hydrogen fuses to produce 1 helium. But here, not hydrogen nuclei themselves, part independently, but there are some, I would say, catalyst, but this word is actually wrong. This catalyst word is applicable in chemistry where atoms and molecules participate. Here we are talking about nuclei, atomic nuclei. Atoms are not there at all in stable structure. But still, this carbon, nitrogen and oxygen, these 3 nuclei takes part in this process. So hydrogen fuses with carbon 12 to form nitrogen 13, which decays into carbon 13. Again, hydrogen fuses with this carbon 13 to form nitrogen 14 nitrogen, which again, fuses with hydrogen to form 15 oxygen, decays into 15 nitrogen, and that again, 15 nitrogen decays into, fuses with hydrogen to form 1 helium and carbon 12. So carbon 12 you get again The carbon 12 which has started the process, you get at the end of the process. So you are neither gaining, you're not losing any nuclei of carbon, nitrogen, or oxygen in general, not always, but yeah. But what you are losing is 4 hydrogen nuclei and you are gaining 1 helium nuclei. So eventually, picture is the same: 4 hydrogen nuclei minus 1 helium nuclei.
Sir,
This CNO side, yeah.
so could you check your audio? I think so. There is a faint echo.
There is faint echo.
Yes, sir.
How can I check that? All of you are muted, right?
Yes, sir.
Uh, should I
V,
disconnect?
I think there is some problem on your side. Sir, your voice is fine. Yeah.
Okay. 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 Yeah. So fine. Yeah. So I was explaining this carbon, nitrogen, oxygen cycle, CNO cycle. So in stellar core, both these cycle can work, either one of them or both simultaneously. PP chain works at comparatively lower temperature in the core. First of all, question comes: why these cycles, why these fusion processes occurs only in the core but not in whole sun? The reason is this fusion processes require good amount of, rather huge amount of temperature and densities. And such high temperature and densities are available only in the core part of the star. So even in that case, the CNO cycle requires much more larger temperature, higher temperature compared to the PP chain reaction. PP chain reaction, takes place even at 4 million Kelvin also, whereas CNO cycle, contributes significantly at 16 million Kelvin. The temperature of the core of the sun is believed to be 15 million Kelvin. So CNO cycle is almost not contributing in case of the sun. But if we increase the temperature of the sun a little, maybe 1 million Kelvin or so, the CNO cycle, contributes significantly. So in heavier stars, heavier than the sun, the CNO cycle is dominating, whereas in case of the stars, lighter than the sun, PP chain dominates. The next part of the structure of the sun is the middle zone between the core and what we say the outer envelope. There is a zone called radiative zone. This zone is called radiative zone because the energy transported through this zone in radiative way. So one gamma ray, the energy emitted in the core is in form of gamma rays. Thank God these gamma rays cannot penetrate the surface of the sun and leak into the space. Otherwise, life would not have been possible on the earth. We are, showered with heavy dosage of gamma rays, and that will not allow life to form. Fortunately, these gamma rays start interacting with this hot plasma made up of mainly proton and electron, and this and also helium nuclei and heavy nuclei is also heavy elemental nuclei. So these gamma rays get absorbed by these nuclei and get re-emitted. But two things happen in this re-emission. First of all, instead of one gamma ray, the nuclei may emit more than one photons of lower energies. So one gamma ray photon is converted into numerous low energy photons. That is one thing. Second thing, this emission of gamma ray may be in any direction in 4 pi steradian. So a gamma ray which was moving in one direction may get absorbed and re-emitted photons will be in any direction. So that's way the energy gets scattered in random walk or in more funny ways, drunkard's walk. So this way the photon does not reach on the surface in the straight line, if it would have reached in the straight line, it would take barely 2 seconds to reach on the surface of the sun. But in fact, the energy produced in the core reaches on the surface after millions of years. Believe me, millions of years of a pocket of energy, takes millions of years to travel this 700,000 kilometers, thanks to this drunkard's walk. And this way, this radiative zone is actually a good reservoir of energy also. So we can say that even today, even at this point of time, the energy stops produced from this core. We will get the radiation from the sun for next few millions of years. Because this radiative zone is keep holding that much of energy. Anyway, that will never happen. But these are the interesting, rather, fascinating parts of this astrophysics. And the third and the last part of the internal structure of the sun is called convective zone. At some point of time, at some place, this photons cannot, get re-emitted because of the opacity. I will not explain the concept of opacity and all, but in technically, it is because of the change in opacity. The opacity is so high. The energy gets absorbed by the material, and the material, instead of re-emitting it, the material, gets heated up, and this heated plasma, becomes lower in density, moves upward like floating. It floats upward, goes at the photosphere, the highest, the outermost layer of the sun. The left side you can see is the real picture of the solar surface. A small part of solar surface is shown here, and you can see some granular structures, some zone or grains you can see. All these grains are basically bubbles of these floating circles. You can see here, in the center of this granule, the material comes up, loses its energy in terms of radiation, and sinks back in the boundary region. So the material which sinks is a little cooler, and hence this boundary is darker compared to the center. So this real picture of the sun gives us the direct clue of presence of this kind of convective cells or convective zones. So this way, the emitted gamma rays, get splitted into various low energy photons in radiative zone, and eventually get absorbed by this convective zone, and eventually get emitted in terms of black body spectrum of 6,000 degrees Celsius or 5,800 temperature from the photosphere of the sun. The structure of the sun is very much required to understand in order to understand the overall evolution of the sun. Before moving to the evolution of the sun, let me tell you something, that the structure of all the stars are not very much same. All the stars have certainly a core which produces energy from fusion of hydrogen to helium. Then from that core, the star little heavier than the sun have, convective core and radiative envelope. The core itself is convective and the radiative zone is outer world, whereas the stars smaller than the sun, say 0.8 solar mass or 0.5 solar mass, they have much larger radiative zone and smaller convective zone. And for very small mass, say 0.2 solar mass or so, they are called brown dwarfs. For this star, almost whole star is convective, and there is no small core. Rather, core is covers almost significant volume of the star. So this way, I want to show how diverse the structure of the stars are. Not only the structure, even their lifespan are also diverse. It's very simple rule. It follows very simple rule. Massive the star, less the life. In case of sun, let us say 1 solar mass, the life is roughly 10 billion year, falling somewhere here. I hope you will be able to see my cursor. Let me move to the pointer option. Yeah. So it is somewhere here. The spectral type of sun is G2. The spectral type basically represents the temperature and also the mass. If you move, towards heavier stars from the sun, the lifespan reduces significantly. Their masses increases from 1 solar mass to say 40 solar mass at O5, or even above 70 solar mass or 80 solar mass or so. We have found some stars with 60, 70 solar masses also. The luminosity, the total amount of light emitted by the star in a second, in a unit time, also increases. Massive the star emits more energy per second, but at the same time, their life become very small. Like the star with 40 solar mass is, 10,000 time small lifespan compared to the sun. Sun lives for 10 billion years, whereas this star lives barely for 1 million years. On the contrary, if you go towards low mass stars, the stars with low mass have much larger lifespan. Like M0 star with surface temperature of 4000 Kelvin or something like that, and with zero point 0.5, half the mass of the sun, the luminosity is barely 8% of solar luminosity, but lifespan is, 560 billion years. Much larger life than the life of the universe itself. So any star of M0 type, let us say, or mass half the sun or even smaller, has not, come to its end, because the the age of the universe is smaller than the life of such stars. So such stars have not yet, came to the end of their life, and these stars are always living. So this way, we cannot, find any stars in the dying phase, which is, of such small masses. Question comes, how do we know how much life this star, lives, how the structure of the star is, what kind of structure of the star is, how they will evolve and all. This evolutionary processes takes millions to billions of years. We cannot probe in the star, within the star or in the sun, to see their temperature, density, composition, and all these things. And how do we know about all these processes which are beyond our reach? There comes the mathematics and computer. We all have studied physics, basics physics principles like hydrostatic equilibrium, the conservation of energy, conservation of mass, and all these principles. And we know their, mathematical formula also. You can see 4 mathematical formula also. Like this formula, dp by dr, this represents the hydrostatic equilibrium, principle of hydrostatic equilibrium. dm by dr represents the conservation of mass. dl by dr represents the conservation of energy, and so on. So these principles, these 4 principles, they are fed into a computer program, and then we, establish a mathematical model. I would say an artificial gas, artificial ball of gas. And then I allow this computer program to evolve this ball of gas, artificial simulated ball of gas, following these physics principles. These physics principles are well understood, well proven. So following these physics principles, how this ball of gas evolves. In the step of evolution, I can decide maybe a million year or tens of million year. So the evolution of sun in 10 billion year, I can finish in few seconds. However, this evolutionary process in this computer takes huge amount of resources and time also, computational time. So that way, the desktop shown here is virtually useless. We need supercomputers to understand the stellar evolution. But what I want to convey is what all we know about stellar structure and evolution is primarily from the mathematical physics and computation. So whatever I'm going to explain is most of the time derived from computer models. At any point of time, I check where this ball of gas evolved, and I check its physical condition like temperature, density and all at various radii. I will see the structure of the star at that stage of evolution. I hope you understand how we know about these details. Like here it is shown at given time at different radii what the temperature would be, what the density should be, the masses and the luminosity at different radii. Okay, so this is the way we know about the stellar structure and evolution. But at the same time, we also directly observe various stars in different stages of evolution. We compare our observation with the computer models, and then we can fine tune our model. So that process is, continuously going. We know good amount of facts about star structure and evolution, and yet we know huge amount of facts about this field. So these are the four principles we follow: hydrostatic equilibrium, energy transport, conservation of mass, and conservation of energy. So with this, I will move to this specific plot, which are called Hertzsprung-Russell diagram or called HR diagram. As I have discussed, the structure of different stars with different masses are quite different. These two fellows, Hertzsprung and Russell, independently observed the stars, and they found that if you observe, tens or hundreds or thousands or millions of stars, and measure two quantities. One is called surface luminosity. Luminosity, when I say luminosity, the luminosity at the outermost surface, and also the temperature, the surface temperature. When I say surface, stars do not have, solid surface. When I say surface, I mean the outermost visible layer of the sun, which is called photosphere. The photosphere appears to be the solid surface, but the density at photosphere of the sun is much, much thinner than the density of Earth's atmosphere. It's 5,000 times thinner than Earth's atmosphere. So surface is actually a fuzzy word. When I say surface, I mean the outermost visible surface, beyond which the opacity is so low that this part of the atmosphere of the stars we can't see. Okay, so if you take observations of temperature and luminosity of different stars and fill this plot, you will see a beautiful pattern. You will see that most of the stars follow a specific trend, a specific line, and very few are scattered in the upper right or lower left region. Let me show you. This is actually the schematic or cartoon of the HR diagram. Let me show you the best available HR diagram to date, obtained by a satellite called Gaia, and this plot is here. Each and every dot here in this diagram is the observation of real star. Gaia observed millions of stars, measured their temperature, measured their luminosity, and they The real purpose of Gaia is to measure the distance of the star, but as a byproduct, we also get the temperature and luminosity of the star. And you can see that this narrow line is filled by most of the stars. Very few stars are scattered here in this upper right region, and very few stars are scattered here in lower left region. See, the y-axis is in log scale, and that is representing the luminosity in solar luminosity. So 1 means the luminosity of the sun. That means sun is somewhere here in this zone. The x-axis is actually color. We forget about that. The color of the star, again, the color in astronomy has a totally different meaning. But instead of this color, you can read temperature. But remember, the temperature is not increasing in scale, temperature is decreasing in scale, like you can see here. The lowermost part is about 25-30,000 Kelvin, whereas the leftmost part is barely 2000 Kelvin. So this part has 2000 Kelvin temperature, this part has 30-40,000 Kelvin temperature. And hence you can see that this narrow strip, the narrow but well-defined strip, houses most of the stars. I would say 90% of the stars. 90% of the stars lies in this strip because for an individual star, 90% of their lifespan, follows a specific temperature luminosity combination. Let us say for the sun, the total life of the sun is 10 billion years. Out of that 10 billion years, sun will spend 9 billion years at a specific small range of this plot. That means for 9 billion years, the temperature of sun is almost around 5800 Kelvin, and the luminosity of the sun also remains constant within few percent. The luminosity of the sun will remain constant for 9 billion years. That means the sun is spending 90% of its time in a specific point of this plot, and that is true for all the stars. All the stars are spending 90% of their life in a given point, and hence at any point of time, if you observe all the stars, 90% of the stars are found in this strip. When they start evolving, they start leaving this strip and moving upward. The points shown downward are called white dwarf. I will explain this object quickly at the end of my talk. I hope you understand this HR diagram. If you understand this HR diagram, not very well, but reasonably well, then only you will understand the next part. The evolution of the sun has very fascinating aspects as well as some technical aspects also. I will try to avoid all the technical aspects, but still I will cover some. Considering the level of the audience, all of you are BSc, MSc students, so you understand basic physics. Okay. Yeah. Here I am showing you two plots. Both are cartoon. One is the graph and another is more like a cartoon. I will explain both these simultaneously to give you what we are going to understand in more detail in upcoming slides. I'm going slowly so that you can understand it thoroughly. Okay. See here, you see this main sequence. Okay, so let me explain this. This main strip in HR diagram is called main sequence. So this is the sequence of the stars. The lower right part has low temperature, kind of 2500, 3000 or 4000 Kelvin temperature. Their masses are also low. Their masses are much less than the mass of the sun. Few percent, 8-10% to 50-70%. And the luminosities are also low compared to that of the sun. The luminosities are 1%, fraction of percent or so. So these stars are low in mass, low in temperature, low in luminosity, and also low in radii. So all these stars are low in everything except life. They are high in lifespan. They spend billions to tens to hundreds of billions of years in their life. When I say they spend life, means they spend in a specific region of this main sequence. A star is called said to be born when it reaches in the main sequence at the point associated with its mass, luminosity, and temperature. So when sun, while in formation process, when it reaches at this point, we can say that now the core of the sun has started fusion process, and hence it reaches in the main sequence. Once it reaches in the main sequence, it will spend 90% of its life. So सन विल सन जब तक मेन सीक्वेंस में रहेगा वो जिंदा रहेगा. सन विल बी कॉल्ड अलाइव till it stay in this main sequence. In the end part of its life, it will leave main sequence. I will tell you. Okay. On the contrary, the upper part of this main sequence are comprising heavy mass stars, heavy luminosity stars, high temperature stars. Everything is high. Size also, radii also high. The only low part is the lifespan. They spend few tens of to few hundreds of millions of years. Okay, so here I am showing this blue strip as a representation of main sequence. The stars are spending 90% of life because for 90% of their life, the hydrogen available in the core continue fusing in huge helium and continue emitting the radiation. This radiation holds the star from gravitational collapse. The radiative outward pressure compensates the gravitational inward contraction. And that happens till the hydrogen in the core available. What happens when all the hydrogen in the core, that few percent volume of the star, eaten up? And in that phase, something interesting happens. The star starts leaving this main sequence. You can see at this point, it is written that H core exhausted. So all hydrogen is exhausted in this core. And then star moves like this, upward, goes downward to this region, and then goes upward, and then goes here. So this is the path of next billion year or even less time span for the sun. Quickly speaking, when the sun leaves the main sequence, its luminosity increases. Its luminosity increases compared to its position in the main sequence because we are watching only upper part. The star is moved in the upper part, that is the higher luminosity. Similarly, the star is moved in the rightward part, that is low temperature. The temperature is low. So we can say while dying, the sun will become cooler and more luminous. How can an object become cooler and more luminous simultaneously? Because luminosity decreases when an object cools down. But the luminosity is certainly, definitely associated with temperature, but luminosity is also associated with the surface area of the star. Because we are talking about the surface luminosity, surface temperature, from where the black body emission, almost black body emission occurs. So we can say that the sun will get cools down and still becomes luminous. So sun will become larger. The size of the sun will increase. The sun will, blot up. How much it will blot up, what it happens, why it comes down, and what happens in this phase when it, suddenly increases its temperature, and then it reduces its luminosity to form a white dwarf. So we will go in this journey. Pardon me if I'll take more time than assigned to me, more than an hour, maybe 15 more minutes. But this journey will be very interesting, and you have never, come encountered this kind of processes in astronomy in your study. The same thing you can see here. I will explain. I will come to this plot again. Before moving to stellar evolution, you may ask me question that what all stories I have explained here, like the stars are in main sequence and it will evolve and all these things. What is the proof that stars are following this kind of motion? What is the proof that the main sequence is actually, a main sequence exists? So one proof I have shown here in the real observation of Gaia of all the stars in our neighborhood. The other evidence comes from the observations or studies of this kind of clusters. You can see, thousands of stars here, but believe me, the span of this region of the space is not more than the size of the moon, apparent size of the moon, apparent size of the moon. If you look in the sky in a very small part, the part smaller than the apparent size of the moon, you will see thousands to sometimes millions of stars. They are called clusters. There are two types of clusters, open clusters and globular cluster. This is an example of globular cluster. Such kind of globular clusters hosts hundreds of thousands of stars to millions of stars of different masses. And if we study all these hundreds of thousands of stars, measure their temperature, surface temperature, measure their luminosity, and plot in this HR diagram. Remember, when I say luminosity, I'm talking about absolute luminosity, but measuring absolute luminosity is very difficult because it requires the information of distance, knowledge of distance. For ordinary star, it is not easy to measure the distance, but for such globular clusters, we know that all these stars of different masses are almost at same distance from us, because this globular cluster is actual cluster in the space. So all these hundreds of thousands of stars are at almost same distance from the Earth. So if we plot them in HR diagram at arbitrary luminosity scale, we actually produce the HR diagram of this cluster, and there you can see that all these stars follow a sequence. Depending on their mass, they lies in different regime of this main sequence. Some of the massive stars have started evolved, so they moved rightward and maybe little upward also. So from this globular cluster, we can actually produce HR diagram, and we get some observational evidences also. So what I am talking about is not the story in the air. It is a story proven by observations. Okay. I say, now let me start the journey of the sun. I say, okay, I will not cover the life sequence of low mass stars as well as the life sequence of high mass stars. They have totally different stories, and again equally interesting, but time will not permit me to go with that. Let us focus on the sun itself. Though I said that sun and all the stars spend 90% of their life in one point only, it is not actually one point. It is a one region, a smaller region in the main sequence. Like here also, you can see that the main sequence has some spread. It is not extremely narrow. It has some spread, some thickness. This thickness comes from various reasons. One of the reason is the evolution of sun in the main sequence also. So during this 9 billion year also, sun is not holding the same temperature and same luminosity. With time, the luminosity of the sun increases and the temperature of the sun decreases. But the decrease in temperature and increase in luminosity is very small compared to rest of the evolution. And also, this small temperature and luminosity change takes 9 million years, 90% out of the life. So sun was not of the same temperature luminosity, let us say 1 billion year ago, and will be little cooler but more luminous after a billion years. So even in main sequence, star evolves. They changes their temperature luminosity. But of course, stars do not change their mass significantly. Even in 1 billion year, the sun will not lose its mass more than a percent. And more than a percent is also a huge number actually. More than a fraction of percent, I would say. After this lifespan, 9 billion years, when all the hydrogen, eaten up by the core, sun reaches here at this point. And there our journey starts. So what happens that you have a core. So this is basically a core. And there the core is made up of pure helium. So now you have pure helium core because all the hydrogen in this core region is, eaten by by this fusion process, and all the hydrogen is converted into helium. So what happens? There comes the picture, the narrow envelope, very narrow, less than a percent in volume of total sun. Very narrow envelope. I would say the skin of the core sphere of the core. The skin of the sphere of the core comes into the picture. The skin part, the outer part, still housing the hydrogen because it is not part of the core, it is outer part of the core. It has hydrogen. Temperature and densities were not sufficient enough to continue fusion process in this outer part during the main sequence. But now, as all the helium, all the hydrogen is eaten up, temporarily the radiation emission from the core reduces, and also this core contracts a little under its own gravity. The reason being the mass of the core, the mean molecular mass of the core is increased. Earlier and now the mass of the core remain virtually same, but number of nuclei decreased because all 4 hydrogen fused into 1 helium. So the number of nuclei in this helium reduced by factor of 4. So mean molecular mass reduces, and this increases. Mean molecular mass increases by factor of 4, less than a 4, little less than 4, and hence this core shrinks a little. And when this core shrinks, it produces energy by gravitational contraction. Gravitational potential energy gets emitted by this core, and that energy hits up this outer hydrogen layer. This layer from now onwards I will call shell because it is a spherical shell around this spherical core. So now at the end of the main sequence life, you have an inactive helium core and now an active hydrogen shell. Though this shell appears thinner, it emits more energy than what was emitted by the core, because the volume wise it is not that thin compared to core, and more importantly it is much hotter now compared to the core when it was in main sequence. So because of high temperature, this hydrogen shell, fusion cell, starts fusing and emitting radiation at higher rate than what was done by the core. More energy means more radiation pressure. More radiation pressure means star has to blow out. Earlier, with less radiation pressure, star was in stable situation in the main sequence at given luminosity temperature. But now more radiation is emitted, so more radiation pressure, so it will overcome the gravitational pull and star will start bloating. It will bloat slowly and will be in quasi-equilibrium at a given point of time. So this represents this point. So from zero age main sequence, so let us say from main sequence, when the hydrogen burning over, the stars start bloating. Star increases in radius and in surface area. Luminosity also increases a little, remember, because the radiation process is higher rate. So luminosity also increases, but temperature decreases because the radius will get double, the surface area will increase by factor of 8 cube, factor of 4 square, because it is 4 pi r square. So surface area will increase by larger factor than that of the luminosity, and hence the temperature reduces. Keep in mind this Stephen's law that the luminosity is sigma 4 pi r square T raised to 4. So the temperature and luminosity always follows this, and you can actually measure the radius of the star from this luminosity and temperature measurement. So this is the structure where hydrogen fusion core is over, you will get helium core, and now in this phase the core begins to contract, temperature rises in the shell. I'm talking about the shell, that will increase the hydrogen burning shell, and hence the star start expanding, luminosity increase, envelope expands, the envelope means the whole star, and the effective temperature decreases. The star reaches at this point and it looks like this. So now inert helium core, hydrogen burning shell, and larger star. The radius of the star increased by factor of 2 to 4 to 10 to sometimes 20 at this point of time. At this point, at this turning point, till this turning point, the hydrogen shell starts, continue emitting energy. But at this point, what happens? Till this point, even hydrogen shell, this hydrogen red color shell, is also, generating helium, and that heavy helium is keep added in the core. So core is keep increasing in mass and mean molecular weight, mean nuclear weight. So in this process, the hydrogen shell keep fusing the hydrogen, and the core, the inert helium core, becoming more and more heavier. At some point of time, the core becomes so heavy that it reaches a limit. This limit is called Schoenberg-Chandrasekhar limit. This is not the same famous Chandrasekhar limit. This is different Chandrasekhar limit. Chandrasekhar has given many theories. His name is associated with more than 10 different numbers, limits, and theories. Chandrasekhar was a giant in the field of stellar structure and stellar evolution. So I'm talking about Subramanian Chandrasekhar, the Nobel laureate Indian origins astrophysicist. So one of his colleague, probably his student, Schoenberg and Chandrasekhar, has derived an upper limit of the mass of the helium core, beyond which this helium core has to shrink rapidly. So Schoenberg and Chandrasekhar has shown that to certain mass limit, this helium core can survive, but beyond that mass, it has to shrink more rapidly. More rapid shrink in core means more production of gravitational potential energy, and that will heat up this hydrogen shell significantly. Heating hydrogen shell means the size of the hydrogen shell increases and also the fusion process, rate of the fusion process. Okay. Suddenly, when this core crosses this Schoenberg-Chandrasekhar limit, the fusion process in the shell increases drastically and star started expanding drastically. You can see here, the temperature is not reducing significantly, but the luminosity increases. More the luminosity emitted from the shell, more the luminosity at the surface. More the luminosity at the surface, the temperature difference is small. So star reaches at this level, and this is called red giant phase. So in this phase, it is called subgiant phase. Why is it? It is subgiant. It is giant because star has bloated up, but still it is subgiant because the real giant is coming now. You know, the size increase in this region is not full in extent. So this is called subgiant. Then this is called red giant. Why it is called red giant? Because the temperature of the star has reduced significantly, so the color of the star appears red. Compare the flame from our gas stove. घर में जो किचन में गैस स्टोव यूज करते हैं उसकी फ्लेम देखिए, और अगरबत्ती जो धूप बत्ती हम यूज करते हैं उसकी टिप देखिए. अगरबत्ती की टिप रेड कलर की होती है, गैस स्टोव की फ्लेम ब्लू कलर की होती है, क्योंकि दोनों के टेम्परेचर में डिफरेंस है. जो अगरबत्ती की जो टिप होती है वो बेरली 1000 केल्विन के आसपास होती है उसका टेम्परेचर, जबकि जो ब्लू कलर फ्लेम हम देखते हैं गैस स्टोव में उसका टेम्परेचर होता है thousands of Kelvin. In fact, sometimes it is comparable to the surface temperature of the sun. Few thousands of Kelvin होता है, so it appears very blue. यही रीजन से, for the same reason, the star of low temperature appears red in color but larger in size. So it is called red giant. So this phase is called red giant. In this red giant, the star is larger in size, low in temperature, and how much large it is in size? The radius of the sun is 50 times than the sun in the main sequence. 50 times in radius. Cube that 50 and that much time in volume. So it is how much? 125,000 times in volume. So sun become much larger. One interesting thing happens here which I want to mention, and that is that at this low temperature, the convective zone, the upper part of the sun, the convective zone of the sun goes deeper. The radiative zone becomes thinner and convective zone goes deeper. एक तरीके से कहेंगे कि जो रेडिएटिव जोन होगा उसके अंदर कन्वेक्टिव जोन अंदर चला गया. That happens because of the change in opacities at different level. I will not go in technicality, but believe me and believe stellar evolutionary models that this convective zone goes much deeper. Much deeper means it goes not exactly to this hydrogen fusion cell, but quite above, little above than this hydrogen fusion cell. More than half the solar radii, 60-70% तक वो डीप चला जाता है. कन्वेक्टिव जोन क्या करता है? नीचे का मटेरियल उठा के ऊपर लाता है. So in this phase, actually, we are started seeing the material which was buried well within the stellar interior. In this main sequence phase, जो ये कोर और शेल के आजू बाजू में जो मटेरियल था, which was rich with heavy elements, नाइट्रोजन, ऑक्सीजन, कार्बन, ये जो हेवी एलिमेंट्स से जो रिच था, और जो मटेरियल रेडिएटिव जोन में फंसा पड़ा था ऊपर सरफेस तक पहुंच नहीं पा रहा था. Now it has started appearing at the surface. So this deepening in the convective zone and dredging up of the inner material at the surface is called dredge up event. So now the material well within the inner part of the sun started appearing in the surface. And if you observe a star in red giant phase, you can see change in its composition. That does not mean that stellar composition changes. That means that the material with different composition in the inner part started appearing in the surface, from where we can see this material. We can detect these different components, different elements in the as a spectral feature in the spectra of such stars. So this is called first dredge up. Why it is called first dredge up? Because more interesting dredge up, second and third dredge up will appear in future. Then at some point of time within the sun something interesting happens. मैं आपको बता रहा था ना, ये कोर है वो श्रिंक हो रहा है. It shrinks, so the temperature of the core itself increases. At some point of time, the temperature of the core crosses a limit of temperature few tens of million Kelvin, and at that temperature, not hydrogen, but helium fusion process starts. Like hydrogen fusion process, helium also fuses to form heavy nuclei. So 3 helium nuclei fuses to form 1 carbon nuclei, and also in that process it also produces oxygen and nitrogen nuclei. So helium nuclei fuses to form carbon, nitrogen and oxygen nuclei. The interesting part here is the sudden increase in temperature at some point fuses most of the helium in the core within a second. Believe me, within a second, let us say 20, 30 or 50% of the helium in this core fuses into carbon. This is one of the rare events happening in astrophysics which finishes in seconds. Otherwise, most of the events take seconds to minutes to years to billions of years. So this is called helium flash. And in this helium flash, the fusion process finishes within a second, and huge amount of nuclei takes part in this process. So the luminosity, the light emitted by this core due to this helium fusion process is billion time or 100 billion time or probably 1,000 billion time, trillion time larger than the luminosity of an ordinary star, main sequence star. एक तरीके से मैं कह सकता हूं कि 1 सेकंड में ये जो जितनी लाइट एमिट करेगा वो लाइट 100 बिलियन स्टार जो हमारी गैलेक्सी में है वो सबकी टोटल लाइट से भी ज्यादा होगा. तो एक ही न्यूक्लियस में 100 बिलियन लाइट यानी पूरी गैलेक्सी से भी ज्यादा ल्यूमिनोसिटी हो जाएगी. एंड मजे की बात यह है कि ये जो इतनी ह्यूज अमाउंट ऑफ ल्यूमिनोसिटी जो 1, 2, 3, 4 सेकंड के लिए जो एमिट होती है वो स्टार के अंदर ही रेडिएटिव जोन में और कन्वेक्टिव जोन में एब्सॉर्ब हो जाएगी. यू विल barely see any increase in luminosity at the surface. पहले बहुत इंटरेस्टिंग इवेंट थी कि सडनली विद इन सेकंड कोर है वो सडनली बिलियन टाइम 1,000 ट्रिलियन टाइम ब्राइट हो गया. बट अनफॉर्चुनेटली वो ब्राइटनेस की इवेंट यू कैन नॉट सी ऑन द सरफेस. So this is called helium flash. In helium flash, tens of percents of the helium in the core gets eaten up, and in that process, the hydrogen shell also burns. But eventually, the star has to reduce its luminosity and also increases its temperature. So at this point, now क्या होगा कि ये जो high जो कोर हीलियम का बना है, that continues fusing helium into carbon. तो मेन सीक्वेंस में जो हाइड्रोजन फ्यूज होकर हीलियम हो रहा था, वैसा ही कुछ यहाँ पे हो रहा है, बट फ्यूल हैज चेंज नाउ. नाउ इट इज हीलियम फ्यूजिंग इन कार्बन. तो ऑर्डिनरी स्टार की ही तरह यहाँ पे स्टार भी मेन सीक्वेंस में से सब जायंट ब्रांच की तरह ये हॉरिजॉन्टल ब्रांच में आगे बढ़ेगा. इन दिस रीजन helium, core helium will get eaten up to form carbon. As you know, more and more carbon fuses, you will get carbon core surrounded by helium and helium shell, and that helium shell like this. यहाँ पे ये helium burning हो रहा है. Like this, you will have onion layer structure. You have inert carbon core surrounded by helium fusion shell surrounded by hydrogen fusion cell. Because of these two fusion cells working at different time and different temperatures, you will get more luminosity, and hence your stellar luminosity suddenly increases. It increases to a level that the luminosity of the star is 1,000 times more than the sun, or sometimes even more. And the radius of the star also increases to 100 times in radii, or sometime more, 200 times, 150 times or so. In volume, it is million times or more. So our sun will increase in radii in this phase. This is called supergiant phase. So in this phase, the solar radius will increase by factor of 100. Remember, the Earth-Sun distance is 100 times solar radii. तो अगर सन 100 टाइम एक्सपांड होगा तो वो अर्थ की ऑर्बिट तक पहुंच जाएगा. वहां से भी ज्यादा एक्सपांड होगा तो वो अर्थ को अंदर ले लेगा. So in this evolutionary process, sun will expand to eat Mercury, Venus, and eventually Earth. It may settle to the orbit of Mars also at the end of its life. Yeah. So it's very interesting process. At this point, the temperature is quite low, the radius is very high. Some pulsation occurs. I will not discuss. The star or the sun starts shrinking and expanding in cycle. It is oscillating. It is called oscillatory motion, oscillates. May not be whole sun, but the core processes, starts in oscillatory motion. I will not go in detail. And in this phase, in this red giant branch and asymptotic giant branch, this is called AGB, asymptotic giant branch. It is called asymptotic because it is very much, in the same slope of the red giant branch, as if it is meeting this red giant extended branch at asymptotically. So this is called asymptotic branch, and this asymptotic giant branch, AGB star, the star here is called AGB star. It is losing its mass, its gas, very rapidly. It is losing its mass very rapidly. Like here, I'm showing you a star is losing its mass very rapidly. Sometimes the star loses its 50% of mass. This type of mass loss is called star wind. Even our sun has also wind. You must have learned in previous lectures that sun is continuously, losing mass in terms of solar wind. But the density of solar wind is very thin compared to this stellar mass, high stellar mass. This stellar mass, this stellar wind is very thick. Of course, not as thick as the atmosphere of the Earth, but compared to other astronomical cells. So in red giant branch, in asymptotic giant branch, the star or the sun will lose its significant mass into the space. In this process, again, the second and third dredge-up processes occurs, and in that way, the produced carbon and oxygen and nitrogen, reaches on the surface and eventually lose by the star in the wind. So this way, this dredge-up processes brings this carbon, nitrogen, oxygen in the interstellar medium, in the free space. So this way, universe is enriched by carbon, nitrogen, and oxygen formed in the stellar core. All this loose material, forms this beautiful planetary nebulae. Sometimes initially mass loss was with low velocity, but eventually high velocity mass will lose by star, and this different velocity masses form the shock, and this shock hits up the gas already expanding in the universe, and this gas start emitting light, and you will see different colorful light. All these pictures you see, these 5 by 6 24 pictures are real pictures. These objects are really exist in universe, and these are the real pictures acquired by telescopes. You can see this planetary nebula. The planetary word is fuzzy word actually. It has no connection with planet. These are emitted by the dying star, and you will see the star in the center of this planetary nebula also. In most of this planetary nebula, you will see stars like this. So these stars have participated, these stars have, passed through the death process, and they have emitted this star. This star this is actually a binary star. This is called Eta Carina. This object is called Eta Carina. This is one of the heaviest star pair we know. There are two stars here. One star is 60 times the mass of the sun, and the other star is 70 times mass of the sun. And they are losing their mass at very rapid pace. So star is losing most of its mass in this space, like this planetary nebula, to give us this beautiful view, and eventually they end up in a white dwarf. So what happened? That the small, tiny, few percent size core made up of carbon, nitrogen, oxygen, and some amount of helium, hydrogen. Most of the time they are, depleted by helium and hydrogen, especially hydrogen. These stars start shrinking. The core, anything above the core is already left in the space. The core part starts shrinking. It will start shrinking. It will shrink to a level from where the nuclei cannot shrink further. This plasma is made up of nuclei and electron. As this object shrinks, these electrons come closer to the nuclei. But we know that all these electrons, can, get infinitesimally close to the nuclei. Or in other words, these electrons cannot come to each other infinitesimally closeness. So there comes the Pauli's exclusion principle comes into the picture. This core starts shrinking under its own gravitation, but it will shrink to a level where all these electrons are settled in the most degenerate state. And that way, all these stars become degenerate. So this star, I will not say star because now no fusion process is going on. So this ball become degenerate. More the mass means more the gravitation, means more shrink, means smaller size. So these kind of objects are called white dwarf. They are called white dwarf because they are very hot. Their temperature is tens to hundreds thousands of Kelvin, and their size is very small. Their size is comparable to that of the Earth. They are Earth size object. Very hot yet very small, so they are called white because hot objects emits all the radiation from red to blue, so they appear white. And they are called dwarf because their sizes are small. So these are called white dwarf. And the white dwarf is very interesting object. They are basically degenerate object. Massive white dwarf have smaller size. As I explained, more mass means more gravitation, means more shrink, means small size. So massive the white dwarf, smaller the size. It's contrary to our routine, experience that massive the object is larger in size. So this white dwarf, the sun will eventually end up in this white dwarf, and this white dwarf will have no end. It will keep, get cooled down by emitting radiation in terms of black body emission. वो जो 100,000 केल्विन का टेम्परेचर था वो धीरे 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 कम होता जाएगा. Eventually it will stop emitting or reduce emitting the light, but that cooling process takes billions of years, sometimes larger than the age of our galaxy. So our galaxy do not have any cool white dwarf. The coolest white dwarf possible in our galaxy has temperature comparable to the sun or little less than the sun, but not few hundred or Kelvin kind of the temperature. So sun will end up in this kind of white dwarf. Here I will take a couple of minutes to explain what happens to the Earth in this process. So as I have explained, in few million years, even in main sequence, I explained that sun is increasing in luminosity. The solar luminosity increases very slowly, even in this main sequence phase. So in few tens of millions of years, within 1 billion years, the luminosity of the sun is that much high, not very high, maybe few hundred Kelvin higher. But even that few hundred Kelvin, few percent higher, but few percent increase in the luminosity of the sun will increase the temperature on the earth. Temperature of the atmosphere and the earth will rise to a level where all the water will get evaporated and you will not get any water in liquid form on the earth's surface. I'm talking about main sequencer. So even before sun starts dying, the life on the earth will get disappear, because without water we will not survive. That's our assumption. By the time we have to leave earth and go to some other planet around the other star where you can live. So that kind of exoplanets we are started searching will take long time, but will definitely hopefully get. So life on the earth will end much sooner than the life of the sun. Eventually, as the sun will pass through subgiant phase and red giant phase, it will expand to Mercury orbit or maybe Venus orbit. The luminosity will be so high and the solar wind will be so high, it will evaporate all the atmosphere of the earth and also evaporate good amount of crust part also, the solid part also. Eventually, the sun will expand to eat earth. Earth will become the part of the sun. And in that process, there are two possibilities. Either the earth itself will get evaporated fully and become part of the envelope of the sun, or the orbiting earth will feel friction from the high density of the sun and solar wind, and so it will lose energy, orbital energy, and it will spiral down inward towards the core and also feel higher temperature, and eventually it will evaporate. So earth will get evaporated before the sun will die. We will be part of the solar envelope, and that envelope will be eventually thrown away in the space. So all the calcium in your bone, all the nitrogen you breathe, and all the iron in your hemoglobin, in your blood, everything in your body, all carbon, nitrogen, oxygen, everything in your body will be part of the sun in end stage and will be part of the universe eventually. This expanded material will participate to form another star, and that's why we are called stardust. We formed from the star because most of the carbon, nitrogen, oxygen, iron, and everything we feel, we are made up of, are formed in a small core of a star or the dying process of even heavier star, the process called supernova. All these heavy and most of these heavy elements are formed from the in the star. Now we are living our life, and eventually all this material will end up merging in the universe. So it's the complete cycle, universe to life to universe via star. With this, I stop the journey of stellar evolution. I hope you have enjoyed. Pardon me if I have covered some technical aspects, but some of you might have found that also interesting. Thank you. Thank you very much.
Thank you, sir, for the amazing talk. You not only covered our own sun, but while doing so, also enlightened us about various other stars and finally touched upon the consequences of the life cycle of sun on the planet Earth. Now, I would request the participants
Give me a
to
minute.
write down their
Yeah, please continue.
yeah. I request the participants to write down their questions in the chat box so that they could be taken up. So we are waiting for the questions to pop up.
Okay, okay.
We have a question on the YouTube.
Please, please.
That,
I suggest you take one question per student so that we can cover more students. If we have some time, we can go for second question from the same student. Yeah, please start us.
Please write your questions in the chat box. Okay, that is the more comfortable way. The question on the YouTube, which has been, it was asked during the lecture, that how are we able to determine that the radiation takes such a long time to come out of the sun? The question is particularly in terms of that gamma rays. That how can we confirm that it is taking billions of years to take?
Okay. So there is no direct way to confirm that the photon emitted in the core is scattered in that random walk in the photosphere, and then the same photon splitted in multiple photons are emitted. So there is no direct observation, but we know the structure of the star. We know the structure of the ball made up of 80% hydrogen, 20% helium, small amount of heavy elements, having the temperature, surface temperature of 6,000 Kelvin and all. All this input we feed in a computer program, mathematical model, I said, and then we try to see what kind of structure this ball comprises of. What our physics suggests, what kind of structure this ball has. So we know about the structure of the star, and if we know the structure of the star, we know how radiation will interact in this kind of as the structure. So most of the information I have explained is basically gained from theoretical understanding. So there is no direct measurement of that. But yes, if we believe in our theory, we believe in these results also.
Yeah.
Next question.
So the other question is that in a life cycle of a star, including from the birth to the time when it is left totally inactive, how many bursts happen throughout, including both radiative bursts and stellar mass ejections?
No, sorry. Will you please repeat the question? I didn't understand that.
In the total life cycle of a star, from the birth to the time when it is totally left inactive, how many bursts happen throughout, including both radiative bursts and the stellar mass ejections?
Burst. Okay. So we need to define what we will call burst. Any increase in luminosity or say sudden increase in luminosity is called burst. I would say thousands of bursts happening continuously every second on the surface of the sun. If we are talking about micro bursts, they are called micro flares. There are major flares also. Daily also we will see some flares in the sunspot active region. We'll see giant flares every century or 1,000 year or million year in the sun. So all these bursts or flares happens on the surface of the sun. We can't count how many bursts happens. This bursting process, the sudden increase in luminosity, is a kind of a continuous process in this evolution. So we can't count. But yeah, major changes in luminosity, size and all, as I have explained, are few like subgiant branch, red giant branch, and asymptotic giant branch. Yes. Next question.
Is there any resources or a YouTube channel or some resource where an amateur can basically learn the astrophysical data processing or cosmological simulations on its own if you want to learn by himself? If there are any resources?
Okay, so there are many resources. I mean, many YouTube lectures on stellar evolutions are available. You just need to Google it. Many standard books also explains this in different details. So you can search for some standard books like Frank Shu or like this Carroll and Ostile. So all these books are well standard books for astrophysics. So they explain all these evolutionary processes along with other astrophysical events. Difficult to point out one because my habit is to study same topic in different books to understand the topic in different perspectives. So I suggest you also not to follow just one book, but try to read the same topic in different books. You will get different insights. Yeah, next question.
Can a black hole or a nearby star affect the life cycle of sun or sun-like star, any other sun? But if it is a nearby black hole or something like a very massive object is nearby sun, how will it affect the life cycle of a sun?
Oh yeah, so any compact object near the star, or not only compact object, even the ordinary star affects each other. So when we are talking about the single star like the sun is the single star, right? Let me tell you, our assumption is 85 to 90% of the stars are in in a group, in a family, either two stars orbiting around each other or more than two stars orbiting in the common center of mass. So they are called multiple star system. Barely 10% stars are isolated stars whom have no any companion. Sun is one of the exceptional, I mean that rare group of stars who has no companion. But if sun would have some companion, maybe black hole or maybe neutron star or maybe white dwarf or maybe some ordinary star, the evolution of sun changed drastically. I will not be able to cover that, but yes, there are chances that if the black hole is reasonably close to the sun or the star, it start eating material from the star or from the sun in a stream way. That material forms a disk around that black hole, and that kind of disks are a good indication of existence of black hole. So this kind of black hole binaries are a good system to find black holes in the universe. Yes.
Yeah.
We can take some more questions if you are comfortable. I have some free time, 5-10 minutes more time available. So you decide.
Yes, fine. Okay. So we will. There are a few more questions. So if you are fine, so we can take them.
Please.
Yeah. As you said that the white dwarf will end in the smallest indivisible part of the sun, then what will happen after that?
So I explained that nothing happened to the white dwarf. White dwarf will float in the universe, in the galaxy. There is no next evolutionary stage known which happens to the white dwarf. It may club with other star or other compact object, but otherwise it's very unlikely, but otherwise it will keep floating. So there is no further evolution of the white dwarf. The only possible evolution is it will lose its energy and get cooled down. That's all.
Yeah. So yeah, so it is a question based on some kind of science fiction. But if you if you want to take, I can ask. Yeah.
You ask the question. Yeah, I will see.
So why should we leave the planet? Instead, we build a stellar engine and move our planet itself when sun starts cleaning the life on Earth.
Please repeat from beginning.
Why should we leave the planet? Instead, when we make a stellar engine and move our own planet when sun starts clearing life on Earth.
I mean, you want to bring whole Earth somewhere else
Yeah.
like this?
Question is if any stellar mechanism can be done.
Yeah, I mean, you are open to think such mechanisms or such machines. I have neither thought nor heard of such things. Of course, imagination has no limits, so one can imagine. But at least in near future, I don't see any possibility of making or harnessing any similar mechanism or anything.
Yeah. One question is from YouTube that do we have any proof of concept that the sudden increase in frequency of solar flares are the symptoms of decaying of our sun?
No, 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 no. As I said, the sun is, almost 4 to 5 billion years to live. So there is no possibility of decay of sun in small time span, maybe a few days or so. As I told you, the stellar evolution takes millions to billions of years. So any measurable change by human in number of flare or anything is due to stellar evolution, solar evolution. No, all this change in
One,
sunspot and all is basically the more local processes.
yeah. One question is in Hindi. The question is, अगर व्हाइट ड्वार्फ में फ्यूजन नहीं हो रहा है तो
हाँ,
उसमें गर्मी कैसे पैदा होती है और वो
हाँ,
कैसे चमकता है?
हाँ, तो व्हाइट ड्वार्फ में गर्मी पैदा ही नहीं होती है। जब व्हाइट ड्वार्फ बना, व्हाइट ड्वार्फ और कुछ नहीं है बट नेकेड कोर है, स्टार का नेकेड कोर है, जो अभी तक पूरे स्टार के अंदर छिपा हुआ था, अभी वो खुल के सामने दिख रहा है। और वो जो कोर था वो बहुत गर्म था, जैसे मैं बता रहा हूँ सन का कोर है वो भी 15 मिलियन केल्विन टेम्परेचर का है। तो अगर वो कोर को ओपन कर देंगे तो इमीडिएटली तो उसका टेम्परेचर होगा 15 मिलियन केल्विन। और मान लेते हैं कि वो जो व्हाइट ड्वार्फ बना, सन के अंदर से जो व्हाइट ड्वार्फ बना, जो कोर है जो एक्सपोज हुआ है, तो उसका टेम्परेचर हाई होगा तो वो हमें दिखेगा और बाद में वो टेम्परेचर एनर्जी लूज करता जाएगा बिकॉज इट कीप एमिटिंग radiation because of black body radiation. So there is no process going on in the white dwarf which emits energy. तो इसीलिए white dwarf है वो energy lose ही करता जाएगा और ठंडा ही होता जाएगा.
Okay. Okay. Thank you so much for this amazing Q&A session.
It's my pleasure.
Thank you, sir.
Yes,
So now I would request Sakshi to propose a vote of thanks on our behalf.
Thank you, Neelbhai. On behalf of Astronomica, the Astronomy Club of St. Xavier's College, Ahmedabad, I would like to thank Dr. Vishal Joshi, sir, for explaining us about the evolution of the sun in such an easy and comprehensible way. I would also like to thank St. Xavier's College and Father Principal Lancelot De Cruz for giving us such a wonderful opportunity. Also, I would like to thank the head of the Physics and Electronics Department, Dr. Rajesh Iyer, sir, and our coordinators, Dr. Sailesh Patel, sir, and Dhaval Bhatt, sir. And I would like to extend my gratitude to Kuldeep Purohit, sir, for guiding us throughout the webinar series, and Neil Bhai for being there with us and hosting the entire event. I would also like to pay my regards to late Dr. Tushar Pandya, sir, for laying the foundation of this club. Last but not the least, thank you all for being such a wonderful audience, and how can we forget all the volunteers of Club Astronomica who work day and night for making this a successful event. Our team members Yash, Arnav, Akshat, Zeel, Divya, Jatin, Ayush, Shubham, Preeti, Mustafa, Kerman, Roser, and Smith. We hope you enjoyed the session and the webinar Antariksh as a whole. Thank you.
Thank you.